Hey guys, here's the second or third video for this lectures, and we continue to cover the electric potentials and find the electric potential of the point. So here's an example for this one, the average density between a protein and the electron in hydrogens. We have a distance, in this case it is r. That's the distance we have, and they ask you to find what the potential of your protein at this distance. So this basically ask you for the volt for this point or for the point. The formula that we have, it is K, and the Q divided by R. So this is our formula. Here is the Q divided by R. And here is the numerical value in this case. Here is the K, 9 power to the 9. With unit in meter square divided by coulomb square times charge over Q, 1.6 power to the minus 19 coulomb, divided by the R. We already have the R by meters, 0.530 power to the minus 10. Minus 10 meter. Just plug those numbers together, you end up with it. Let's see the unit. We have here is the meter, meters. Okay, coulomb square. What else? The M, so the Newton, meter, and coulomb. Okay, so we end up with the number is 27. Here is the volt per, yes, volt, sorry, don't have any volt. Volt, the Newton by coulomb is a volt divided by coulomb. So here's the Newton per coulomb, what's the electrical field, or we can type it volt divided by M. And we have from this part, the top here is the M. Cancel this one with this one, will end up with 27 volt. Now the second question, similar to that one. The only thing here is that we have Van de Graaff generator, has 25 centimeter diameter sphere, and the accumulated charge about 1.5 micro coulombs at the surface. What the potential on the surface of generator? So it's the same thing here is for the sphere and the charge around the surface. So here is the V at this point here, the same formula, equal K, and here is the Q divided by R. Here is our value right now. Here is the 9 power 9 Newton meter squared divided by coulomb. So you don't have to memorize all those numbers. When in the exam, those constants will be provided for you. Times charge that we're given right now, 1.5. Here is the 1.5 micro minus 6 coulomb divided by, be careful this one, This one, it is diameter, so I have to divide it by 2. So here basically 0.25 meter divided by 2. You end up with the numbers here 1.1 power to the 5. 1.1 power to the 5 volt. Okay, let's see the situations when we have a couple of the chargers, they are distributed around and they ask you to find the electric potential at certain point. So right now they ask you to find the electrical or potential at this point. We have 3 charges. So we have here is, let's number them or give them a titles. Here is the number 1, here is the number 2, and here is the number 3. Okay. Now we need to find, because the equation that I will use, it's basically this V total. It's equal K, just summation, Q1 at the position number 1 divided by R1 divided by R1 plus K, Q2 divided by R2 plus K, Q3 divided by R3. So right now I have charges, K is constant. I have to identify the R1 and R2 and R3. Here is the R1. In that case, situation is here, 4 centimeter. 4 centimeter. R2. Where is the R2? Here is the R3. Let's type it first. 2 centimeters. And here is the R2, which basically root square of 4 square plus 2 square. You end up with the 4.47 centimeter, 4.47 centimeter. So this is the R2. Now I have all the information that I need, so I can find my total volt here. I'm gonna take the K outside. Here is the K. Q1 divided by R1 plus Q2 divided by R2 plus Q3 divided by R. I have the informations. K, it's basically 9.0 power to the 9 as the unit column in Newton, meter square, column square. This one multiplied by Q1. I have to type the Q with the charge. Q1, it is minus 5 power to the minus 9 column divided by R1. R1 I have here is the 0.04 plus second the Q or the Q2 10, sorry, 10 power to the minus 9 column divided by the R2 0.0447 meters and plus the third charge, it's 5 power to the minus 9 column divided by R3.02 meter. This 3 terms. So the addition for those 3 value end up with the 3,200 volt. So how it's easy, you don't have to, because the electric potential is scalar, so you don't have to consider the charge or the direction. So it's just the additional or add the formula, the charges and the R's together. Okay. Second point here, the question here asking to find what the electric potential energy of the electrons. The electrons here is pointed, here's the electrons, and we have two charges. They are protons, and they are the distance around 1.5 nanometers. And to find out electrical energy, from the formula that we have, here is the electrical energy. We call it, give it a U, electrical energy or electrical potential energy. You can call it electrical as your textbook mentioned. Here is the electric, which basically is just a Q or the charger type V. Let's call it, here is the total. So which basically here the electrons here, I need to find how much electric potential first. Once I found the electrical potential at that point and I have the electron charge, I can find my energy or electrical potential energy. So now I have to identify the total in this case. And the total comes from the two positive charge, which basically I will use the formula. Let's assume this one is number 1, this one is number 2, and this one is the R1 or R2, sorry. And this one is the R1. So basically the formula Q1 divided by R1 plus Q2 divided by R2. Now, Q1 equal Q2. In this example in particular, R1 equal R2. So we can manage that situations here. We end up with the V total. Just I don't want to repeat the numerical twice. So basically Q and the Q and R and R, so all of them. So basically this one is the double K Q divided by R. Let's call this one is the Q. Let's call this one is the R. Where is I have all the information. Now I can use my electric potential. Here is the 2. Here is the 9 power to the 9 Newton meter per coulomb. Here is the Newton meter square per coulomb. Per coulomb square. 1.6 power to the minus 19 coulomb divided by R, 1.5 power to the minus 9 meter. According for this calculations, you end up with the 1.92 volt. Once we find the electrical potentials here, so now I can find my electrical potential energy, which basically just Q times V. Here is the Q times V. Q times V. Okay. What happened to my computer? I hope. Okay. Go ahead. Okay, good. Times V. I have all the, I have V and have a Q. And here you end up with the value minus 1.6 power to the minus 19 times 1.92 volt I end up with the result minus 3.1 power to minus 19. Minus 19. In this case, here is the joule. If you want to type it by electrical or the electrovolt, basically it is 1.92 electrovolt as the energy. Okay. Basically, we are almost done. So the last part here, regarding for the cardiology, when you just represent the cardiac or the what we call it the EKG as electrical potentials. The inside and outside, the inside is positive charger and the inside is negative charger. They create electrical potential in between to let the hearts work in a proper way, and they give you the signals or the familiar signal, what we call it the PS or RST wave, and just kind of the application for the electrical potential. I don't want to speak longer than that, and I will end up with this point. Thank you.